So good morning, everybody, or good afternoon, depending on which part of the world you are currently in. So today we are privileged to have David Prendergast to be our speaker. He'll be talking about X-ray spectroscopy as a probe of electronic structure. I'll just tell you a little bit about David and then we can start. Meanwhile, during the talk, you can ask a question, but at the end also, we'll be able to bombard David with many of the questions you have. If you want to, you can chat also, type a question in the chat and we'll take the questions and give them to David. So David is a senior staff scientist and facility director for theory of nanostructured materials at the Molecular Foundry, a department of energy nanoscale science research center at Lawrence Berkeley National Lab. So he received his PhD in physics from the University College Cork in Ireland, and then he joined the Foundry as a staff scientist. He's interested in X-ray science at the advanced light source and using X-ray science to probe many materials. In particular, he is able to connect what we do, electronic structure, together with what experimentalists measure. So he'll be talking to us today again about X-ray spectroscopy as a probe of electronic structure. So over to you, David.
Great. Thank you so much, Omo, for that nice introduction. And thank you very much to EAIFR for the opportunity to present to you. I really appreciate that. And I hope you enjoy the seminar. So let me just start by doing a little bit of introduction. And hopefully you can see my pointer, right?
Yes, we can see it. Thank you.
Okay, let's go. So, okay. As Omo mentioned, I'm going to talk about X-ray spectroscopy today. I'll start by briefly introducing just the concept of a user facility and what it means. Many of you may have used user facilities before, but if not, maybe it's helpful for you to understand how that works. I'll then, after describing X-ray spectroscopy, try to connect it to electronic structure theory and how we actually simulate that measurement. Then I'll talk about how these kinds of measurements can reveal dynamics in materials, either at finite temperature or in the ultrafast regime. So that would be, let's say, processes that occur in less than a picosecond. And then I'll talk about many-body effects and provide some outlook. Okay. So first of all, where I work at the Molecular Foundry. So this is a user facility that provides state-of-the-art multidisciplinary expertise, methods, instrumentation for nanoscale science. So just to give you some context, back in the, let's say, early to middle 2000s, the US government started what was called a Nanoscience and Nanotechnology initiative. And as part of that program, they began the establishment of 5 different nanocenters across the United States. And the Molecular Foundry was one of the first, and it's located in Berkeley in California. So by definition, nanoscience is a multidisciplinary field. It requires understanding objects at the nanoscale, and that involves the intersection of many different fields, including energy, electronics, material science, biology. And I just have some picture examples of some of the work that's happening inside the Molecular Foundry these days. But it really is trying to push the boundary of what we can do at the nanoscale. Okay, and as a facility, it has access to expertise in different areas, including synthesis of different kinds of materials, fabrication of materials, as you'd see in a, let's say, in a microelectronics company, characterization of different kinds, surface science, as well as electron microscopy. And then, very fortunate for me, it has a theory facility embedded in the middle of this that allows people to make predictions, to try to understand nanomaterials, how they behave, to explain the phenomenology that is observed in experiment, and to come up with new ideas for new materials and new applications of nanoscience. So in the theory facility currently, we have 4 staff members. There's myself. You'll hear about my research today. Steve Whitelam is my colleague who works on non-equilibrium statistical mechanics and also some machine learning. Liang Tan is an expert in photoexcited systems, systems out of equilibrium, and also 2D materials. And Sinead Griffin is an expert in material science focused on correlated oxides, multiferroics, and even something as exotic as dark matter detection. And maybe you'll get an opportunity to hear from some of those folks in the future as well in this very nice forum. So as a single institute, we have a pretty big impact because we are a user facility, and I'll talk about what that means in a second, but you could think of that as our collaborators. And in the best of times right now, and I hope you're all doing well, but during this pandemic, we're not exactly running at full speed. But back in 2019, we would have been serving about 1,000 users per year with various statistics here. But that said, you know, the world is not perfect, and it's probably painfully obvious to some of you that, you know, access to scientific facilities is not evenly distributed, it's not equitable. And I would say we have very few users from Africa at all, you know, given what a huge continent that is. That's pretty sad. And so hopefully an event like this is a way to reveal to the African science community what we have to offer. First of all, that it's free and that it's collaboration based. And given the current climate that we're in right now, where we're all used to Zoom every day, somewhat, then, you know, distance is not so much a factor anymore. So collaborations can occur over the internet, especially for theorists. It's quite natural for us to do that. And so I'd encourage any of you, if you're interested, to think about the Molecular Foundry and what it might have to offer you. Our user program has 2 proposal calls per year. Anyone can apply. They're pretty short proposals. They're only 2 pages. They're externally reviewed. Typically, a project is expected to last up to 1 year, but we encourage people to renew their projects. And if it's non-proprietary, meaning you intend to publish the work, then it's free. And if you invent something, that's also owned by you. And so, yeah, our next call, if you're interested, is at the beginning of March and closes in April. And then the next call will be 6 months after that again. And I talked with Omo, and he said we can post these slides online. So wherever you see a link in the talk, if you have access to the slides later, you can click on that and learn more about what's on the slide. So the Molecular Foundry is one of multiple user facilities at Berkeley Lab in California that include a supercomputer, a Genome Institute, and several research collaborations that are dedicated to things like energy storage, so batteries, solar fuels or artificial photosynthesis, water desalination, hydrogen storage and generation, the kinds of things you'd expect a Department of Energy in a government to care about. Today, I'm going to talk mainly about my interactions with the Advanced Light Source, which is our local synchrotron, and I'll try to explain briefly what that is. So, okay, what is a synchrotron? It's basically an accelerator that's run in a circle. And so you accelerate electrons around what is not quite a circle, it's actually a polygon. So at the vertex of the polygon, there are magnets that can bend the pathway of the electrons, and that acceleration causes them to emit radiation. And if they're going fast enough and you accelerate them fast enough, then that radiation that's emitted is in the X-ray range. So X-rays have energies from, let's say, above 100 electron volts in the soft X-ray regime up to maybe 100,000 electron volts at the very end of the hard X-ray regime. And most likely what you're most used to hearing X-rays about, let's say, what they're useful for would be doing diffraction studies. So looking at crystal structures, using Bragg diffraction to learn about crystallinity in materials. And probably most recently, X-ray crystallography has been vital as a resource to learn about the coronavirus and its structure and how it interacts with our own biology. The ALS is not unique. There are many synchrotrons around the world, and there's a list of them here. And so there are plenty of opportunities for collaboration, and we'll see that later on. All of these facilities are generating data every day. Again, you'll notice that there isn't a strong presence of any synchrotrons within, let's say, the African continent, but I'm very happy to see a a continuing effort to develop an African light source. And the most recent meeting involved around this topic was in 2019 at the University of Ghana. You can read about that here as well later, or you can Google it. But who knows, maybe in a decade or so, there may be a light source also in Africa that would be useful to you scientists as well. So what good is a synchrotron? What good is an X-ray source? So I already mentioned that X-ray measurements, they're often used to study atomic structure using crystallography. But you can also use X-rays to probe electronic structure through spectroscopy. And so keep in mind, obviously, that advancing technology relies on a deep understanding of electronic structure. Physics, chemistry, material sciences, earth sciences, biology, they all use X-ray spectroscopy to reveal local electronic details. And I'll explain in a second why that's the case. And then beyond the science need, you know, an X-ray light source or any user facility, it's more than just a big building. It can multiply its impact on thousands of users per year. So not just the staff who work there, but the people who come to visit it, to use its facility and then leave again and take their results with them. That has a really lasting impact and a very broad impact. And then from a theory's perspective, a facility like this can be supported virtually or remotely through data interpretation or even experimental design. And from my personal perspective, and hopefully some of yours as well, electronic structure theory is really vital to understanding X-ray spectroscopy. And that's what this talk is going to be mostly about. So in brief, if you were to shine high energy X-rays on a material, or even accelerated electrons, although I won't talk about the equivalent measurement using electrons today, but think about this picture on the right-hand side here. So here's an image, a schematic of a band structure, and there's some valence bands, so some occupied electronic structure and some unoccupied conduction bands. And then they're deep down in energy, there are these core levels that we usually don't think about, that are typically inert. They don't contribute to bonding or to chemistry or any material properties usually. But if you have enough energy in your photons, you can kick electrons out of these core levels and into available unoccupied states in the conduction bands or the unoccupied molecular orbitals if you're looking at a molecular system. And so if you think about the size of the orbitals involved, so the core levels are really, really finely localized around individual atoms. And then you're exciting into a very disperse and wide-ranging valence electron cloud. So it gives you an opportunity to learn about that more widespread electronic structure with a very fine and highly focused viewpoint from the perspective of an individual atom. So to give you a specific example, so if we were looking at carbon, we could think about exciting the 1s electrons of carbon into available empty states. Now, as you go across the periodic table, what you would notice in optical absorption is several jumps, or what are called edges, as you cross the threshold to begin to excite the core electrons of those particular elements. And nature is very kind to us here because it has separated out the elements roughly every 100 electron volts or so. So if you have a spectrometer that can easily resolve these energies, then you can learn very much only about one element at a time within a given sample. So that's very useful. Just some terminology. The letter K is used to denote excitations of 1s electrons. L for the second quantum shell, either 2s or 2p electrons. M for the third quantum shell, and so on. And so if you see me, mostly in this talk, I'll refer to what's called the K edge, like this carbon K edge, nitrogen K edge, oxygen K edge. These are excitations of carbon 1s electrons, nitrogen 1s electrons, oxygen 1s electrons. And there are tables online, like this website here, where you can look up the energies or characteristic energies of these different edges. And that helps in designing experiments, but also in designing calculations as well. So this mathematical expression here is a manifestation of Fermi's golden rule for X-ray absorption. And so it connects some initial state, typically the ground state, through the dipole operator to final states, and then filters those excitations based on the energy difference between those two states, whether it matches the photon energy or not. By definition, due to the Pauli exclusion principle, you're kicking electrons out of available occupied states into unoccupied states. And so you're probing unoccupied electronic structure. That's unlike photoemission, which probes occupied electronic structure. So X-ray absorption would be telling you about your conduction bands or your unoccupied orbitals. And then, as I said already, you can look at elements one at a time. So it's element specific. And then it also follows a dipole selection rule very strongly, because intrinsically these transitions are atomic-like, since they come from the core orbitals that are localized on the atoms themselves. So if you want to think about it mathematically, since the dipole operator is an odd function, right, R changes sign as you move through the origin, then if you excite from an even function, you can only excite into an odd function. And so the dipole selection rule tells us that the angular momentum value can change by ±1. So for k-edge excitations, for 1s orbitals, we can excite into p character in the available unoccupied states. So to put that in more context, imagine you had a system that was comprised of a molecule, let's say, embedded in water, so a solvent, and you only wanted to look at the molecule. Well, if it had different elements than water, so carbon in this case, you could tune your X-ray energy to align with the 1s excitation energy of carbon, and then begin to steadily excite at different energies, first of all, to reveal local molecular structure, as the excitations are localized around that particular site. And then eventually, as you go to higher energies, more about the environment around that molecule. Okay, but I keep drawing pictures over here on the right-hand side that look like band structure, and that's because you have to remind yourself that you are directly probing electronic structure. And so that's where the value of an electronic structure technique comes in here. We can use that to interpret these measurements. Okay, so what would I need in my toolkit as an electronic structure theorist to try to understand these spectra? So just breaking down the Fermi's golden rule expression here, I need some knowledge of the excited state energy spectrum. I need the energies. And then I also need to evaluate transition amplitudes here. And so therefore I need states, I need wave functions. Now there's an alternative approach which says you don't need wave functions, and I'm not going to talk about that here, but a friend of mine, Professor John Rare at University of Washington, has a very famous code called PHEF that uses what's called real space multiple scattering to directly access the Green's function of the electronic system. And you can rewrite this expression in terms of the imaginary part of the electronic Green's function. And that can tell you directly about X-ray excitations as well. But we're going to focus on wave functions in this talk. So if we used a single particle approximation, which band structures like this kind of imply that we can do, so we're transitioning from one orbital into another orbital, you can write this as a transition from the core orbital into some final state orbital, with the energy difference defined between that final orbital energy and the initial core orbital energy. And if we're using density functional theory, then we could, in principle, calculate those different orbitals and their energies using the Kohn-Sham equations. So some Hamiltonian acting on our final state orbital with a given energy. Okay. Now, it's important to understand that there's pretty strong final state effects in X-ray spectroscopy. So let's start on the top here. Imagine you have some initial state. So I've made an idealized crystal here of atoms in a one-dimensional line, and each of those atoms has its own atomic orbital. So think about this as, you know, the picture you see in textbooks of linear combination of atomic orbitals that make up the ultimate band structure of your material. And valence electrons in this picture, they experience an effective nuclear charge equal to the atomic number minus the number of core electrons. So that's your effective Z. And if you use that analogy, then the core excited state changes the number of core electrons. It excites one of the core electrons. So that number goes down by 1, which means that the effective charge of the nucleus is going to increase by 1. So that's referred to as a Z+1 approximation. And what would that look like in this one-dimensional picture? Well, that one atom that you excited now looks like it has a greater charge and therefore creates an attractive potential well for electrons to localize around it. And so this is what leads to very strong excitonic effects or trapping effects for the electron hole pairs that you create when you excite this atom. And so what you'll notice is that your band structure no longer looks like it did originally in the ground state, but it has some impurity levels that were introduced due to the presence of this instantaneously modified atom in its excited state. So you can think about X-ray excitations as a way of instantaneously creating defects in your crystal or in a molecule in such a way that it creates defect states that you can then understand by interpreting the spectrum. Okay. And so what will be the consequences of that in different materials contexts? So in a molecule, electron hole binding will shift the energies of your orbitals. If you want to think about it in this single particle picture, you could imagine the unoccupied molecular orbital being pulled down in energy nearer to the core orbital that you excited. If you have a more complex molecule with multiple electronic levels that are close in energy, they will mix and hybridize differently as they move around in energy. Perturbation theory tells us that. And then if you have an extended system like a crystal, you can go from a ground state that has completely delocalized bands that have a very small effective mass to completely localized, infinite effective mass bands, flat bands that sit in the band gap of the material. And so that really begins to look like this defect picture that we're used to from semiconductor physics, where an atomic defect inside a semiconductor lattice can introduce mid-gap states, as they're called, or color centers, or some kinds of defect in the electronic structure. And so X-ray excitations do that as well. And just keep in mind that core hole excitons, given that the origin, the core orbital that defines the hole, is much more localized, then the exciton itself is much more localized than the corresponding valence excitation might be. So using density functional theory, where we can define the total energy of the system as a functional of the overall electron density, we can exploit the approximation that was introduced by Kohn and Sham to solve this problem, where the electron density is defined as a sum of the densities of a non-interacting fictitious electron system that has the same electron density as the overall ground state system that you care about. And in this case, what we treat as a variable are the occupancies of these orbitals. So, whether you realize it or not, you have a choice, right, in which orbitals that you occupy to define the density. And usually we use what's called the Aufbau principle, meaning we occupy these electrons one at a time, starting with the lowest in energy and working upwards, because as fermions, we can only occupy each orbital once. And we do that in order of energy to satisfy thermodynamics. But in this excited state, you could imagine almost in a like a binary code here, right? If you had initial occupations that were all ones and then empty zeros afterward, if I flipped these bits and created a hole in one of these orbitals and moved that excited electron into the first available zero, then I could define an occupation that might represent the core excited state accurately. Now, this is a pretty gross approximation, but it actually works quite well, particularly for these 1s excitations that I'm going to focus on in this talk. So this is schematically what's represented in the band structure on the right here. We place a hole in one orbital and put the electron into an available orbital. At self-consistency, if you do this in the normal DFT self-consistent cycle, so you update the orbitals such that the orbitals stop changing as the electron density converges, then you can reach a situation where the difference in energy between the excited state configuration and the ground state configuration is a pretty accurate representation of the overall total energy difference between the ground state and the core excited state. And also that electron density captures a lot of the electronic relaxation that would occur in the core excitonic state.
David, please, I have a question.
Yes.
Suppose you don't do delta SCF and you just take the difference of the orbitals. How good is that result?
Usually not so great for this reason. So you'll be missing certain states that just don't exist in the ground state. So in a crystal, for example, if it's a truly periodic system, you have Bloch orbitals, they're completely periodic. And without breaking the symmetry of the crystal by producing this core hole, you could never realize these localized excitations. There are other ways to generate the same excited state electronic structure instead of using delta SCF. You could use perturbation theory, and I'll talk a little bit about that later. But really, it's quite a strong perturbation. So yeah, the ground state would not be a great choice.
Okay, yeah. Thank you. Yeah.
No problem.
Hi, David. This is Do. You have a question regarding the delta SCF procedure. So
Sure.
in the defect physics, and people normally need to consider additional tricks that to make sure the convergence of the total energy when you have a charge defect. So here, in addition to increasing supercell size, do you have anything else need to consider to ensure the convergence?
Yeah, I'll talk about that shortly, actually, just very briefly, but it's a good point, do you? Let's see here. Yeah, it's coming up on this slide. So if I answer your question, fine, and if I don't, you can let me know, and I'll try to provide more detail.
Sure, thank you.
Okay. So as I said, when you make this, let's say, perturbation in the electronic structure and relax it electronically, what you're doing is allowing all of the electronic structure to feel the presence of this core hole. So you're making a static approximation that the excitation is long-lived enough that the surrounding electrons can notice it and react to it. Now, if you want to do this practically, as Dayu mentioned, you should try to model this excitation not in your, let's say if you're doing a crystal, not in your typical unit cell, because that would mean that every such atom in that unit cell and all the others was excited, which is not the physical case, right? Physically, X-ray scattering or X-ray absorption has a very low cross section. So you're typically only exciting one atom at a time in the, it could be approximated as an infinite crystal. And so we try to do that using a supercell, so multiple unit cells, which is a bigger calculation, but typically only about the size of a nanometer, so 10 angstroms. That's sufficient. So if you can, that's maybe 80 to 100 atoms for most crystals. So it's a doable calculation. It's not the typical cheap calculation you can do for a small unit cell, but it's doable. And then there are some practical implementations that you might require. So if you're using an all electron approach, like in quantum chemistry or LAPW, something like that, there are methods that allow you to prevent your numerical solution from collapsing onto the ground state. So one such method is called the maximum overlap method that's developed within the quantum chemistry community. And there basically you relax your electronic structure subject to a constraint that the orbitals that you are occupying don't change too much, okay? In addition, if you were doing a plane wave calculation, you don't even have core electrons, right? You can't even access the core electrons because they're buried in the definition of the pseudopotentials that you might use to describe the electronic structure and scattering off the nuclei. And so in that case, you'd have to develop your own core hole pseudopotential. So remake a pseudopotential where you use an electronic configuration that looks like this, has a hole in one of the deep orbitals. And that's actually quite stable. So because you just have a different potential, again, it's very much like treating an impurity in the overall crystal. You change the identity of that one atom to make its excitation and put a different pseudopotential there. And then finally, this delta function here, this is not a great approximation where you estimate the energy difference as the difference in orbital energies. That would be what's called Koopman's theorem, which is not exact in this particular case. And so what we do is rely on the fact that we have a really good approximation to the electron density and use the total energy difference between the excited system with its excited density and the ground state system with its density. And that works quite well for energy alignment. Okay, hopefully that answered your question, Dave. So here's an example of just how it might work in practice. So this was a study we did looking at different copper oxides. So Cu2O, so copper in a +1 state, and CuO, copper in a +2 state. And we used the oxygen molecule as a way to calibrate the energy of our calculated spectra if we were focusing on making excitations of oxygen atoms, okay? And then down here is the simulation of what the spectrum might look like for CuO in green, Cu2O in red. You can see indicated here the size of the supercells I use. They're not too large, only 32 atoms in the copper oxide case. And in the cuprous oxide case, 162 atoms, so a much bigger unit cell. And then the experiment on the right-hand side. So it's not too bad. It's not perfect, but it's not too bad. And we can then go in and analyze each of these peaks since we have the wave functions, look at the wave functions and understand what is the character of these peaks, meaning what kind of electronic structure contributes to them. Okay, so that's just a proof of principle that it should work. But now, let's say you have this tool, so you can reliably reproduce measured spectra for a given atomic structure. So consider that like a black box, okay? If that works, then you have the freedom as a theorist or a computational scientist to propose new models, any kind of atomic structure that you like, any kind of electronic state, and begin to propose those models as ways of matching, let's say, some changing experimental condition or some unknown feature, let's say, that exists in a measurement that people don't understand. You can throw whatever you want at it and try to see if you can mimic that case. And so that gives us a large application space in functional materials, which typically change over time or do something that alters their atomic structure or their electronic structure. X-ray spectroscopy allows us to see that. And if we have the tools, we can interpret those kinds of changes as well. So this was an early example on looking at carbon dioxide capture inside a porous material, a so-called metal organic framework or MOF. And in the experiment, basically they're measuring here at a particular energy that corresponds to exciting 1s electrons of the magnesium atoms inside this MOF. And so what they did was they went from vacuum to increasing pressure of CO2 and then back to vacuum again. And what they noticed was that there's this feature here at the beginning of the spectrum, at its absorption edge, that decreases in intensity as you absorb CO2 and then comes back again when you remove the CO2. And so in our calculations, we were able to collaborate with folks that we knew at the Molecular Foundry, Jeff Neaton in this particular case, who had already looked at the binding of carbon dioxide to this particular magnesium site in this metal organic framework. And when we computed the excited state electronic structure and then the spectrum, what we noticed was that, yes, indeed, there was a peak at the edge of this spectrum that was intense initially, but then when you add the CO2 molecule, it goes down in energy. And then we were able to explain why in terms of restoring symmetry at this site, but you can read about that in this paper. So this kind of sets a good example for how this might work in practice, where you can propose an atomic structure or a model that you think might explain the situation in the experiment, simulate the spectrum, and then see if that is indeed the case by looking at the experimental data. Now, let's keep in mind that that opens up a lot of possibilities for us as theorists, because we think about things in terms of individual atoms often. And so, you know, even though an experiment might look at an entire system, which means it's kind of an average over many atoms, our calculations will tell about each individual atom and what it might contribute to the overall average spectrum. And that's very useful for techniques that combine X-ray spectroscopy and microscopy. So if you can focus your X-ray beam down to a size that's maybe on the nanometer scale, these are 3 different examples here, down to 30 nanometers or 20 nanometers or even 5 nanometers. Now you can use your very detailed calculations to try to explain the different features that might be observed in this combination of spectroscopy and microscopy. So these images here, these are false color images associated with particular features in the spectrum measured at each individual pixel here, the pixels being 20 nanometers in width. And this is looking at the edge of a molybdenum disulfide nanoflake. And you can even begin to see what look like different layers here. And these edge features had some different spectroscopy than the overall bulk of the nanoflake. And we were able to explain that in this case as defects in the edges of the material by just creating those defects in calculations and simulating their spectra. So I'll give you a great example of somebody who has used this technique to really define their research. So Sarvajit Banerjee is a professor now at Texas A&M, and we've been collaborating with him through the user program at the Molecular Foundry, where he came to us and said, look, I have this data, I need to understand what it means, and that worked out to be a great partnership. So 10 years ago, we looked at graphene, and what doesn't look like a very flat or very uniform material, but it turns out that as prepared, this material had lots of corrugations, it was rippled, and we were able to see those ripples as changes in X-ray absorption, mainly due to the fact that it should have a very well-defined spectrum if it's flat, but if it's curved, you'll see variations in intensity, as we were able to show in our simulations. We've also looked at candidate materials for battery cathodes, so energy storage materials. Vanadium oxide was one. And then catalytic systems as well. So this molybdenum disulfide system I mentioned before was useful in producing hydrogen electrochemically. And so we were able to understand maybe that there are defects at the edges of this particular crystal that allow the system to catalyze the production of hydrogen in acidic solutions. So in this case, he's an expert in nanomaterial synthesis. He uses this nanoscale X-ray spectroscopy to look at his materials. And then we, as electronic structure theorists, can come along, try to model these systems atomically and electronically, and connect around this kind of measurement to try to understand what's happening. Okay, so I've talked about maybe how you would see functioning materials in terms of their defects. So what's going on inside them that might be different from the overall bulk behavior that would be visible then in a spectroscopy measurement. But it turns out that even non-defective materials can also have spectral defects, and that's what I'm going to call them, and I'll explain what that means in a second. And you have to keep in mind that core level excitations, they occur really, really quickly on attosecond timescales. And so that means that if you think about the Born-Oppenheimer approximation, where you imagine that the electrons move much, much faster than the nuclei around which they revolve, you might capture an out of equilibrium situation, even though on average the system is at equilibrium. There's all kinds of fluctuations that can occur inside a material on very fast timescales. And if you have a probe that can see on the very fast timescales, you might catch the system out of equilibrium and learn something about it. So this could be something as simple as finite temperature fluctuations, or even 0-point motion that's always present, that might be visible in spectroscopy. So why is that? Well, I already hinted at the Born-Oppenheimer approximation. So if I could imagine the total state of the system as being a direct product of its electronic component and its nuclear component, then the electronic transitions are only impacting the electronic part to a rough approximation, let's say, especially for X-ray excitations. We'll ignore the fact that the nuclei might have charges. And so the dipole transition operator here defines the transition. But then if I expand the overall transition amplitude based on the Born-Oppenheimer approximation, what I'll see is that the first term in this expansion has the dipole transition and an overlap between the vibrational wave functions. And if those overlaps aren't perfect, what you'll see are fringes in your absorption. So regions where you absorb, regions where you don't. And that's called the Frank-Condon effect. It's very well known and exploited in optical spectroscopy as well. So you get to see vibrational energy levels individually. If you continue this expansion, let's say varying some coordinate q, which would be related to the nuclear system, then the first derivative of the dipole operator appears here, and a new dipole-like term for the nuclear coordinate. And so this is the first term you would see if you have a transition that's not allowed. Let's say the dipole rule is not satisfied, and mu here is 0. And so this second term here is referred to as the Hertzberg-Teller effect, and that would be the dominant term if you have a dipole forbidden transition. So that gives us kind of a clue for some interesting physics if we look for things that should be hidden. So here's an example in a small symmetric molecule. S-triazine has 6 atoms in a ring here, 3 nitrogens alternating with 3 carbons. It's very symmetric, and it has lots of symmetry planes that happen to have, you know, almost no electronic weight on them. So there's a symmetry line along the plane of the molecule here, perpendicular to it, that separates electronic structure on either side. There's that orbital actually has no weight on the nitrogen atom if we were to excite it. And so the blue spectrum here indicates no intensity when we simulate it at this particular energy of this LUMO +1. So the orbital that's just above the first unoccupied molecular orbital. And then similarly, the LUMO +2 is kind of flat here, but also has no P character on this nitrogen atom. So it's also dark or doesn't have any intensity. However, if we distort the molecule, it's hard to see, but I've kind of displaced some of the atoms here. So the symmetry isn't perfect. It doesn't have mirror symmetry anymore. Now we begin to see that these transitions become a little bit bright, meaning they have some intensity. And so in real life, if this molecule is sitting in a thermal bath, it's going to be moving around all the time, and its atomic structure is going to be varying. And these particular peaks will be visible in an experiment. And that's indeed the case. You can read about it in this paper. So that gives us an idea for maybe extending this to solids. So many salts, many crystals that involve cations and anions are often described by electronic structure that looks like what's on the right-hand side here. So the anion in the crystal has all the electrons and the cation has given them up. So by definition, the first unoccupied states would be cationic states. So in magnesium oxide, the first empty orbitals would be magnesium orbitals. And then based on their electronic structure, if they're from the far left-hand side of the periodic table, or let's say not transition metal atoms, not open shell, more often than not, these first excitations will have S character. Okay. So now, if we were to make X-ray excitations from the 1s orbitals of this atom, of the magnesium, or any cation in this set, 1s cannot make a transition into another S state, right? That's forbidden by the dipole selection rule. You have to go to P character in this case. And so that implies that there may be dark states in the X-ray absorption spectra of many of these kind of simple salts. And you can look for them in experiment. And so I have an experiment here in the dashed line. Hopefully you can see that. This is for lithium fluoride, rock salt. And what you see is that this very strong peak here has a pre-edge that's pretty bright. And it turns out that if you model the crystal with no perturbations, so let's say not really 0 Kelvin, but with the, no 0-point motion either, the atoms are clamped in place and they don't move, you'll see that the very first excitation, this blue box around the lithium atom in its center, it definitely doesn't have any P character. It's inversion symmetric. And so there is a dark state that defines that excitation. If you do the simulation, you'll see that it doesn't have any intensity in the X-ray absorption. But then if you run molecular dynamics, the local distortions around that site, they don't necessarily turn it into a P state, but the symmetry is not quite perfect. And so what was a very symmetric box that matched the cubic symmetry of the crystal is now more distorted. And you begin to see some weak intensity appear here. And as you increase the temperature, this intensity grows and it begins to look more like the experiment. And so in, let's say, most materials, dynamic disorder, the materials overall are not disordered. They might be highly symmetric, but on a very, very fast time scale, if you were to take an image of them, all the atoms would be slightly out of place. And so dynamic disorder and those kind of defects can cause some spectral features that you can look for. And so it's a very interesting way to learn about dynamics in materials. In practice, what we do, if we want to model the spectra of systems that may have some interesting dynamics, and not just solids, maybe systems that truly have dynamics like liquids, we use molecular dynamics simulations to capture multiple snapshots of the system in time. And then we average the spectra computed for each one of those snapshots and combine them together using the computing facilities that we have to generate an overall average spectrum that hopefully matches experiment. And the idea here is to mimic what happens in the experiment, because in the experiment, you expose a sample for a certain period of time. In the volume that's exposed, many atoms get excited. They all contribute to the absorption spectrum, and that's what we're trying to mimic here. So actually, the very first example that I had the good fortune, let's say, to look at was a study of liquid water. And this was our best attempt at the time, back in 2006, to understand the differences in spectroscopy between liquid water and ice, solid water. And it turns out that the spectral features in these particular examples followed the hydrogen bonding structure within the liquid and the solid, which are quite different. And we were able to interpret them in the measurements as well, based on these differences. So in terms of fractions of broken hydrogen bonds versus unbroken. We've moved on a lot since then and started to look at non-homogeneous systems. So we're particularly interested in interfaces, since most of the functioning aspects of materials occur at their interfaces. And so thanks to lots of experimental developments that are happening simultaneously at Berkeley Lab, allowing us to look directly at X-ray spectroscopy of interfaces, we've been able to explore many different aspects of, let's say, functioning electrochemical systems. This is kind of a high school example: platinum as the electrode and sulfuric acid as the electrolyte. This is what would produce hydrogen if you were to bias the platinum electrode. And the measurements are shown here as a function of voltage applied to the electrode. And then our simulated spectra are a little bit different. What we did was we examined each of the chemical species that might be present in the electrolyte, both near the interface and in the bulk. Everything from hydronium ions, which are the acid part of sulfuric acid, sulfate anions, bisulfate, which is a protonated version of sulfate, sulfuric acid, and then water in its various no donor, single donor, and double donor hydrogen bond cases. And then using those spectral standards, which you can't actually see in experiment individually, we were able to combine them in different linear combinations to reproduce the experiment and understand the relative concentration of different species at the interface, learning that sulfate is highly concentrated at the interface, and actually local pH converts what should be at the interface, which is bisulfate, into sulfate. So that was quite interesting. And also we noticed from our measurements, we didn't see any intensity at these low energies, which would have been indicative of oxidation of the platinum electrode, which is something that's in textbooks that should happen under these conditions, but we don't see any evidence for it here. And so our simulations were one way to validate that, yes, if you had oxygen adsorbed on the surface or OH on the surface, you should see peaks at this low energy, but they don't appear in the experiment. So we can say that at least in this experiment, there's no evidence for oxidation of the platinum surface. Okay, so hopefully you're getting a picture for how, you know, a typical application of electronic structure theory and understanding the dynamics of materials might be turned into an interpretation of an experiment. And I talked about dynamics at finite temperature. So the previous system was a liquid, meaning it was, you know, constantly changing as a function of time. Imagine if you could kind of stop events and then start them at will. And that's kind of the basis of what's called pump probe spectroscopy, where you can, with a light pulse, initiate an excitation and then follow it a little later by using another probe that's correlated in time with the initial pump. And so this is an example, not using X-ray absorption, but using X-ray photoemission. I just want to use it to serve as an example and an introduction to this topic, where we were able to use an X-ray free electron laser. So this is the linear coherent light source at Stanford, to look at changes in the core level binding energy of a ruthenium atom, which is here inside a dye molecule attached to an oxide surface, to zinc oxide. And there were 3 hypotheses in the literature about what the first excited state of this molecule looks like at a certain moment in time after you have excited it with light, so with visible light. And one idea was that it's still on the molecule. So let's say at a time scale of about a picosecond, it hasn't left to move into the oxide to do something useful for you. Let's say if this was part of a solar cell. Another theory was that, no, it's gone. You won't see that electron anymore. It's gone into the oxide and it's doing something useful. And so the molecule is ionized. And then the alternative is somewhere in the middle where you have an interfacial state created where the hole is left behind on the molecule and the electron sits just beneath it in the surface. And so by creating these 3 different possibilities, in theory, we could then simulate their core excited states and figure out what the binding energy differences might be. And it turns out that obviously the middle example here is the one that matches experiment. So this is just an indication that we could use excited state electronic structure to mimic dynamic effects, but it gets better. So if we think about the fact that, yes, X-ray spectroscopy, the individual excitations are fast enough to see dynamics, then static spectra, what they are doing is something equivalent to what's called long exposure photography. You might see beautiful images like this where the image itself is obviously static, but it implies that there's motion because you've basically left the camera open for a long time, and it has these kind of ghostly images of what might have been happening over time as the water here moves over these rocks. And so that's what normal static X-ray spectroscopy is doing. The system is not static. You're collecting an average, and if there are some rare events, they appear as these kind of light features or wispy features or weak peaks in the intensity. And then the more static objects appear very strongly. And so if you can use dynamic simulations to mimic that behavior, you can also interpret that spectrum. Alternatively, you can look at movies, right, where you define a time origin and a series of, let's say, snapshots in time where you're following the dynamics in the system. And so this is an example of one of the very earliest movies that were ever made. This was commissioned by Leland Stanford, who wanted to settle a debate about whether all a horse's legs left the ground while it was galloping. And so they set up cameras along a racetrack and took pictures of a jockey here riding by. So you can use a pump and a probe. So a pump to define the origin in time, and then a probe some specifically defined time later to measure dynamics, and do that using X-rays as well. And so that allows us to see ultra-fast processes, dynamics below 1 picosecond, where the electrons might not be at equilibrium. And all the things I mentioned before about exploiting the Born-Oppenheimer approximation, that may not apply anymore. But it allows you to maybe see things like bond breaking, non-thermal melting, maybe even destruction of magnetism due to photoexcitation. So some very exciting physics in there. And in addition, ultrafast spectroscopy is an older field that has been studied using optical pulses and infrared pulses for many years. If you use X-rays, the added advantage is that you can now follow individual atoms, so local electronic structure. Okay, so it would take an entire talk to go through all this in detail, but I just wanted to mention some particular methodologies here that you can use to explore real-time dynamics. So you can use the kind of static approach and prepare different states of the system and then see how they would differ spectroscopically and try to match that with experiments. So our original delta SCF approach would apply there. You can also use time-dependent density functional theory and even many-body perturbation theory. So the Beta-Saltputer Equation coupled with the GW approximation. But for excitations in the time domain, there is a formulation of time-dependent DFT that runs in real time, where you can create, let's say, a time-varying electric field or potential and look at how the electron density responds in real time. So that's very appealing for looking at dynamics of systems as they evolve on the kind of attosecond to femtosecond timescales. This is just an example of something we were able to accomplish using time-dependent density functional theory. in collaboration with Professor Steve Leone, who's at the UC Berkeley campus. And it was looking at a small molecule, cyclohexadiene, which exhibits what's called ring opening dynamics when you shine light on it at 266 nanometers. So formally, the free energy landscape looks like this. There's an excited state potential energy surface that you slide down. There's a conical intersection. And eventually you can reach some stable state where the molecule has opened up. And then you have a choice. It will either go back to its original state or it will move on and fully dissociate. Or sorry, break apart as a ring into a linear molecule. And so this is an example of, let's say, following the bond length as a function of time, sorry, here, and seeing in multiple simulations how it can split and increase or go back to its original ground state. And then also looking at populations of different states that define a simulation of the spectrum here as a function of energy and a function of time. So these are different peaks in the spectrum changing in this kind of very fast time regime below 100 femtoseconds. And the way we did this calculation was a combination of time-dependent density functional theory and what's called fewest switches surface hopping, which is a technique that allows you to jump between these different potential energy surfaces based on kind of a guided random sampling that says how likely it might be that the electron might jump around once it's excited. So like I said, I can't go into every detail on this, but it's very exciting that we can also access these experiments. And these also don't require a synchrotron. Professor Leone does these experiments using a laser setup in a small scale lab. More recently, what we've been doing is studying more complicated molecules. Although this is a smaller molecule, methyl iodide also has some complicated electronic structure because of the heavy atom here, the iodine. And if you shine light on this system, it will emit its iodine atom. It will break the bond between the iodine and the methyl. And so in this case, we had to go beyond density functional theory and use so-called wave function methods from quantum chemistry, mainly because the excited states in this case are multi-reference. So you can't define them as a single electron configuration. They're better defined as a linear combination of different electron configurations. And there is software out there that will allow you to do that. So we combined a standard open source quantum chemistry code, OpenMulcast, with a freely available surface hopping code that allows us to model the excited state and its time evolution. And then we converted the output of that calculation to tell us what the time varying spectroscopy might look like on this kind of femtosecond timescale. So these are doable calculations for sure. And what this implies is, we're changing our approximation here. So if we go back to Fermi's golden rule, now we have a better approximation for what these wave functions might be. And so using wave function approaches from quantum chemistry, we can describe those many-body states using Slater determinants, something like configuration interaction or active space methods to build up a very large expansion of those particular electronic states. Okay, so this will be the last part. I realize time is marching on here, but hopefully I have time to maybe conclude with one small extra piece and then I'll stop. Is that okay, Omo?
Yeah, this is fine. Yeah, thanks.
Okay. So, okay, quantum chemistry methods, and the reason I'm not talking about them here is that they're fine for molecules, but they're really, not applicable to solid state systems because those methods scale very badly with system size and are maybe sometimes ill-defined for an extended system. So what could we do in that case? So I already mentioned the Beta-Saltputer equation. This is one way that we can model excited states that comes from many-body perturbation theory, where in this case, we explicitly write the final state here called phi f as a linear combination. A here is just a constant of the creation of electron hole pairs with respect to the ground state. So you have your ground state orbital that's made up of, your ground state many-body state made up of multiple electrons, and you end up creating a hole. So sorry for the mixed notation here, that's actually destroying an electron and then creating the excited electron in an available empty state. And then some linear combination of those excitations represents the best approximation to the final state. And you can solve an equation to find what those eigenstates of the excited system are. This is called the Beta-Saltputer Equation. This is well-defined for valence excitations in a paper by Stephen Louis and Michael Rolfing. But for X-ray excitations, it had already been figured out by Eric Shirley, who's at NIST, the National Institute of Standards and Technology in the US, in this 1998 Physical Review Letters paper. Okay, so this is very similar to time-dependent density functional theory. Actually, the equation that you solve here is analogous to time-dependent density functional theory, except what's different here is your definition of the electron-hole interaction kernel. Okay, so I wanted to talk about a particular example where Beta-Saltputer works reasonably well, although not perfectly, and our original approach that I described earlier fails, surprisingly, and I'll explain why. So these are different transition metal oxides: titanium, vanadium, chromium, manganese, iron, and titanium again in a perovskite structure. And what we noticed, oh, is there a question? Maybe not. Okay, what we noticed was that our simulations consistently underestimated this first peak in all of these spectra. So the black are the experiments and the blue are our simulations. And so this is kind of surprising. We've been doing really well for, let's say, non-transition metals. And now suddenly, as we go into this family of materials, we're doing pretty badly in predicting their spectra. And so, okay, what's wrong here? Furthermore, if we did Beta-Saltputer calculations, they begin to restore the intensity of this first peak. You can see comparing, let's say, blue to red. This peak is low, then gets high, low, high, low, maybe, yeah, this is the same. And so this was kind of disappointing because we were very happy with this core hole approach. First of all, it's cheap, whereas Beta-Saltputer is more expensive. And Beta-Saltputer doesn't scale very well, so it's not really viable for all of these studies we've been doing of dynamical systems where you sample many different configurations for large supercells. So this was, worrying. And even still, Beta-Saltputer is not perfect. It doesn't quite match the experiment exactly. Let's say the ratio of these pre-edge features and the main edge is not quite reproduced well enough. So, we scratched our heads and tried to figure out what's going on here. And it seemed quite strange to us that this core hole approach that had worked so well in the past seemed to have the opposite effect that we would have expected. So you have an experiment that has a sharp peak at onset. And then if you put the core hole into your calculation with delta SCF, as we described, you reduce the intensity. And normally you would expect that it creates a localized state that has more overlap with the core orbital, and therefore that enhances the intensity. And indeed, even without any core hole at all, you have a lot of intensity here for these first transitions, but it disappears when you include that perturbation. So why is that? Okay, so if you think about a schematic here that looks like a ligand field model, where you have an oxygen atom interacting with a transition metal atom, and they maybe make bonding and anti-bonding states. Okay, it's just a schematic. The final state picture for the X-ray excitation deepens the local potential, let's say, at the oxygen. So all the previous spectra were exciting the oxygen atoms. And so this orbital energy is going to come down, and that will maybe increase the gap between the bonding and anti-bonding orbital. Furthermore, if we look at the orbitals themselves, in a quasi-ionic system or a polar system like this, the oxygen has most of the electrons in the occupied orbitals. The transition metal atom is oxidized, it loses electrons. And so what you'd find is that the occupied orbitals are mostly oxygen in character, a little bit transition metal if they're hybridized. And then the opposite is true for the unoccupied orbitals. Now, if you were to excite the system and drag down in energy this oxygen 2p, what you'd find is that, yes, the occupied orbitals get more oxygen character because the electrons are more localized in that deeper potential well. So you make the system more ionic, you reduce the hybridization with the d orbitals. But then as a complement to that, the unoccupied orbitals do the opposite. So you have even less character on the oxygen state and more 3D metal character. And so now this defines, let's say, the problem in our previous calculations. So there's a cause, meaning you fill this orbital when you make the excitation, and then the presence of that core hole and the electron together lead to this effect. Okay? And so if I was to come in afterwards and measure, well, okay, what's the probability of going from a 1s orbital on this oxygen into this particular state that has very low oxygen character or very little weight on the oxygen atom, then the intensity is going to be low. But that ordering of events is incorrect. It's like I've made the excitation and then I assess the X-ray absorption. Whereas in fact, the probability should be determined by the first thing, which is you go into an available orbital and then the system responds and alters its electronic structure. So we have somehow mixed up the time ordering. So just to put that in perspective, the initial state has a set of available orbitals that you could occupy if you were to make the excitation. So that's what the, let's say, for want of a better word, what the core orbital sees as possibilities for excitations. And then afterwards, once the excitation is made, then the electronic structure is modified. And that defines maybe the energies of the excitations that emerge. So we kind of need to do two things. We need to define our excitations in the initial state and then project those excited states onto this kind of final state picture that we've relied on so well in the past. Okay, so there's a lot of detail here, but I'll just go through it quickly. If we can define the dipole operator in terms of creation and destruction operators for the initial state, so make a hole and fill an electron in some available empty state. And then we also consider expanding let's say, that excited initial state, right, where you've created n electrons that are in their ground state orbitals and one additional electron in available empty state. We could do something similar for our final state, expand that in terms of creation operators. And then we have to recognize that these systems have two different sets of orbitals, right? They come from two different sets of fields. What we'll need is some kind of transformation matrix that gets us from one set of creation operators to the others. And so that's all mathematically definable. We can do the excitation in this order, make it first in the initial state, then project onto the final state, and then that defines our transition amplitude. Okay, so you can read about the details of how we actually did that here. It turns out that our transition amplitudes are actually defined to be determinants in terms of this transformation between the initial state and the final state, if we also define our wave functions to be determinants. And so it gives us a nice way of capturing the many-body aspects of an X-ray excitation. It's not just from one orbital to another. This transformation involves all the orbitals in both the initial state and the ground state. Okay, so bottom line, does it work? And it does. So you can look here at the red curves are the new calculations using this many-body formalism, and the blue curves are the old ones just using that delta SCF approach. And you see this first peak gets more intense in every case, and strikingly so for this one example, chromium dioxide, where there was almost no peak in the core hole approach due to this effect I talked about, where the weight of the electronic states shifts away from the excited oxygen. But in this case, they get quite intense when we correct for that with this many-body effect. You'll notice here that I have two curves in the simulated spectra, one called F1, which means I include only single electron hole pairs. With this determinant formalism, I also have the option to include two types of excitations, single electron hole pair and double excitation, so two electron hole pairs, the core hole and its electron, and then maybe a valence hole and its electron too. And it turns out that helps restoring some of this intensity after the first peak, which is a closer match to experiment actually. And you could keep extending this to many excitations, but usually two electron hole pair excitations are sufficient. Okay, so short story, it works. And we won't go into a lot of detail on that right now. So let me summarize quickly what we discussed today. So I introduced X-ray spectroscopy to you and its applications. It has wide-ranging applications across all the sciences. And just to remind you, it's a very local probe of electronic structure, of chemical state, even of magnetism. I didn't talk much about magnetism in this talk, but it's also used in that context too. I described to you how you would do those simulations using density functional theory to start with, and the delta SCF approach, meaning you explicitly model the excited state and treat your core holes as static defects. This allows you to see material defects in spectroscopy. And then we also explained how you can use molecular dynamics to see defects in time. Also to explore interfaces in materials and as they function. I gave one example of an electrode and electrolyte. And then you can extend that analogy because of the speed of these excitations to chemical dynamics, so truly electronic dynamics, where you can see even bond breaking. And then I concluded by talking about how maybe sometimes delta SCF is not enough and you need to go beyond, let's say, the single particle approximations embedded within it and think about many body wave functions and how that can be helpful in the example I gave to describe transition metal oxides. I just want to kind of highlight something. So, you know, X-ray spectroscopy, from my own personal experience, I found it to be extremely helpful in helping me understand electronic structure. And my group members feel the same way, that, you know, even though we do lots of different studies using different techniques, quantum chemistry, density functional theory, molecular dynamics, studying ultrafast processes, energy conversion and storage, solution phase chemistry, all of it is underpinned with this particularly, you know, useful measurement technique, X-ray spectroscopy. And so almost all of these different projects have some X-ray spectroscopy aspect to them. And, you know, it's doable. You can do this too if you have an interest in it. All you need is what you have already, maybe good atomic structural models and their associated electronic structure. And then you can derive this delta SCF excited state for each atom, generate your simulated spectra, and then check to see if your model of the material matches in terms of its spectroscopy what you see in experiment. So it's something for you to think about if you're interested in this research. You can interpret the measurements made by your colleagues, for example, or you can even go out on your own and predict and design future experiments that would be successful based on your calculations. And we're finding as well, you can even validate your understanding of electronic structure theory and how accurate it might be. And so I just want to emphasize that working at a user facility as I do, that's something we offer, which is training and consultation in how to do these kinds of simulations. And I think we've successfully done that in the past, even with our experimental colleagues, to help them make sense of their own data. With that, I should thank all of my collaborators, both on the theory side and the experimental side, and then the funding for this work, which mostly came from the United States Department of Energy. I work at the Foundry, but we also make use of our supercomputing resources at NERSC, and my colleagues at the Advanced Light Source, who did many of the experiments that we mentioned here. And thank you for your attention. And I'll leave this previous slide up here as some inspiration for you.
Thank you very much, David. Thank you very much.
Okay, you're welcome. Thank you.
So we'll take some questions. So if you have questions, you can unmute yourself and ask. In the meantime, David, I have a question.
Yes.
So you see that in this picture, say the TiO2 one on the top right, delta SCF and Beta-Saltputer, they get the same energies, right? Excitation energy. It's just the peaks that is
exactly
wrong. Okay. So my first question is, why is that? That if you can do so well for the energies, how come the intensities which depend on the wave functions is not correct? And then the second thing I want to ask is, how much should we trust experimental peaks? I mean, intensities. Yes, the position of the peaks, I think, is pretty much well established. But how much would you trust the intensity from experiments?
Okay, great questions. Let's take the first part. So you notice something very important here, which is that the delta SCF approach is actually really good in the sense that for these core excitations, a static approximation for their impact on the electronic structure is actually pretty reliable. And to be very fair, right, it is taking Fermi's golden rule to its most literal interpretation, right? You couple initial states directly to final states, right? And so, you know, as most physicists do, right, you think about something that happened in the beginning and something happens at the end, and you forget everything that happens in between because it doesn't matter. And so those energies come out to be pretty accurate, particularly for the spacing between the excitations and even the character of the states. So you can rely on that. And if you only cared about the energies, I think you'd be in good shape. You could make a good approximation for the spectrum. However, oftentimes, you know, what look like distinct peaks here are not just single orbitals. There may be many orbitals in this energy range. And so if you had a lot of these energies, it could be very difficult to understand if you had a good Max-J experiment at all, because, you know, maybe, let's say in this energy range, there might be, I don't know, tens of states, maybe even 100, but only some of them are X-ray active. And so it might not be an easier thing for a solid or a condensed phase system to directly interpret the energies that come from delta SCF as peaks, because actually there's so many of them that you do need the intensity to help you kind of pick out which ones are important. Okay, so that's one challenge. And then the reason why the intensity is so much brighter when we include the full or some approximation to the many-body aspects of the transition is related to something I described here. So it's about time ordering.
Okay.
If we don't, if we let's say if we cause the effect, so we make the core hole in delta SCF, we have altered the electronic structure, and so now it's too late to ask, well, how probable those transitions are, because they've already happened. The change has occurred, and in this particular example, it has reduced the intensity on that excited atom. So therefore, that's why the intensity is so small. Okay, hopefully that answers your question in a short space of time. With respect to the experiment, initially when you start in this field, you have to presume that your experiments are good, right? Because otherwise there's no hope. And so you work through, you know, trying to make sense of the measurements that you have with the calculations you can do. I'll tell you, at some point you get some confidence in how you do these simulations and how accurate your results might be. And you get to a point where you begin to realize, yes, there are some mistakes in the literature. And there's even some surprises. So let's say something is labeled as an oxide, but when you do the simulation, you find, nope, it doesn't look anything like that. And you find out that actually the experiment had some impurities on its surface. And actually it was a carbonate, not an oxide. And so when you do your simulations, you have that freedom to try anything and see if it can make sense of the experiment. Similarly, you might find peaks at the wrong energy, and it turns out you have to calibrate the experiments in the same way that you have to align your calculations. And so you can help your experimental colleagues also understand if they've made mistakes. But overall, I would put it in a positive sense that, you know, it's not always the case that we know exactly what we're looking at. And so this combination of experiment and theory can be very helpful to unravel mysteries that we might see in the experiment.
Okay, thanks. Yeah.
Hi, Omololu?
Yeah, go ahead.
Yeah, so I'd like to ask to David a question, and if you can go back to the slides about the photo dissociation and maybe the slide just before.
This is of the time-dependent measurements?
Yes.
Okay, I'm almost there. So these methodologies and this one, yeah?
Yeah, and maybe the slide also, which is just before this one. So yeah, I have trouble understanding the kind of information you get from X-ray spectroscopy for these specific dynamics. And okay. I've learned quite rarely the mention of X-ray spectroscopy when people were discussing photodissociation. So I'm a bit curious about your input here.
Sure, yeah, and I apologize. I didn't have enough time to go into this in detail. So let me explain. Okay, so let's look at this schematic here. So these are the potential energy surfaces for the ground state as a function of the stretching of a bond inside the molecule. So this is what you'd expect, right? It costs you energy to stretch the bond. But if you're in an electronic excited state, let's say you made a transition from the HOMO of the molecule to the LUMO, then you might be on a different potential energy surface, which would be forcing this bond length to increase. Okay, so if you create this excitation, simple optical spectroscopy will be able to follow this energy difference, right? And as a function of time, you might see that the position of the excited state energy decreases. And you could interpret that pretty easily with a small molecule like this. Where it gets more complicated is if there may be many atoms in the system, optical, let's say, ultraviolet or visible spectroscopy, it directly probes molecular orbitals, but not localized detail. So a molecular orbital might cover the entire molecule, which means you're kind of learning about what is happening in a small region of space, the breaking of a bond, through what's happening to the entire molecule all at the same time. And so it's not as specific in teaching you about what's happening when the bond breaks. Whereas X-ray spectroscopy, which makes excitations from deep levels that sit far below this potential energy surface, those excite individual atoms. And so if you pick the right energy, you can focus on a particular atom. Or even if there are two atoms of the same element, both doing different things, you can see that difference in this time resolved spectroscopy as well. And so it's a very nice way of getting an element specific or atom specific window on this dynamics to learn more about maybe how the dynamics proceeds by interpreting the experiment.
Okay. Okay. I guess it's describing those papers that are mentioned on this slide.
Yeah, if you have more questions, you can also email me. I'd be happy to explain it in more detail too.
Okay. Thank you.
You're welcome.
So there was a question also in the chat about any free code or recommended commercial code that can be suggested for photodissociation. Yeah. Okay,
so I mentioned these two pieces of open software here. And what we have done to calculate X-ray absorption on top of this is something that you can also figure out how to do using OpenMolCAS. We have a Journal of Chemical Physics paper, this one here, reference 3, together with Michael Odelius, who's a professor in Stockholm, who developed methodology inside OpenMolCAS to do core level excitations. And so for those of you interested in quantum chemistry, you can use that software definitely to reproduce results like this. Yeah, maybe a more in-depth tutorial will be more appropriate to that, but also this paper is pretty clear, and we didn't use anything beyond open software to do this. In the extended systems, we're typically using Quantum Espresso, so open source DFT code, and there is already in Quantum Espresso this X Spectra technique that you can use. We do something slightly different, but it's basically not that different. And then our Manybody version is actually available on GitHub as a Python post-processing step after we do Quantum Espresso calculations. So that one, since it's more complicated, we're still developing it to become more user-friendly. But as I mentioned at the end, if you wanted to learn about this or to have training in how to use it, that's something we offer for free. So you know, either through the user program at the Molecular Foundry, you could come and learn how to do that or do it remotely with us. Or maybe there may be opportunities in the future with a workshop to explain exactly how those calculations are done.
Okay. David, a couple of things. What if somebody is interested in experiments and wants to shoot the beams himself? Is
Good
there
question.
possibilities for that?
Yeah, so all the synchrotron experiments that I mentioned, so all the ones that happen at light sources, those are user facilities.
Okay.
So, you know, okay, the process is similar to how we work in that people submit proposals, they're reviewed, and then if they're approved, you get to travel to that facility and do the experiment there with the help of the staff.
Okay.
Usually that goes a lot better if you get in touch with the staff beforehand.
Okay.
One thing I mentioned at the start of the talk is that, you know, while it might be that certain facilities are, let's say, heavily oversubscribed, there are many synchrotrons around the world. So let's say in East Africa, you could consider maybe there's a new light source being developed in Jordan called Sesame.
Yep.
There's also in India some light sources as well that might be closer, or even in Brazil, Sao Paulo. I know that's quite a long distance, but they're maybe not as heavily used as some of the facilities in Europe and the US. So you might have a greater opportunity to do your experiments there. But again, it's an open process, you know. It's just obviously it's hard to get initial experience to prove your point that you could do the experiment.
Okay.
But a lot of these facilities have fellowships and opportunities to support travel. So there are ways to do this if you're interested.
Okay. Yeah. So thank you very much, David. The second thing is there are some of us who would like to discuss with you about collaboration.
Okay.
So I think it would be good. We could end the talk now, and then people that are interested in discussing with you will stay behind and discuss with you.
Okay, no problem.
There's
And then,
a question, there's a question from Peter Ngene. Could it be that for the platinum electrode described, the formation of surface oxide layer on the platinum is difficult to probe experimentally? So
okay.
yeah.
That's a great question. Let me go back to that part. Yeah. Here we go.
Yeah.
Yeah, it's a good question. For sure, it's difficult, and the experiment itself was kind of a really challenging experiment to realize. We're only in the last 5 years or so figuring out how to do experiments that are extremely interfacially sensitive. So I didn't talk about the experimental detail, but on the left-hand side, this is what the experimental setup looks like. On the left, you have vacuum, and then this region here is a liquid cell that's protected from the vacuum by being surrounded. Inside this window that allows X-rays in and out, there is a deposited electrode, that's the platinum, and then the electrolyte is the sulfuric acid, and you have control of the liquid to flow it in. And if there's some damage that the X-rays may cause to the liquid, you can replenish it by continuously circulating this here. And then there's some counter electrodes embedded in here as well to allow you to actually create the electrochemical conditions of having a potential difference at the surface. Okay, the way the experiment is realized is actually exciting with X-rays, but then detecting not the fluorescent X-rays that come back, but emitted Auger electrons, which come from a very narrow region within maybe 1 to 2 nanometers distance from the surface. So on this scale, this is one of the few examples where my simulation actually is a close approximation to experiment in terms of scale. Let's say down to about here is about 1 nanometer. And so what we're expecting in this experiment is that it's sensitive only to the oxygen atoms in this region. And so if there were an oxide on the platinum, it should be very, very sensitive to that, because if the oxide builds up on the surface, it's even closer to the electrode, and it's the actual electrode that detects the signal. So let's say if I excite an oxygen here, it goes into an X-ray excited state, and then that state decays or relaxes and emits an Auger electron that might be detected in the electrode or might be neutralized by an electron coming in. It depends on how the process works. And so the closer it is to the electrode, the stronger the signal might be. And so if if anything, this kind of experiment should be extremely sensitive to the presence of an oxide on the surface, just because the oxide is pinned to the surface itself, and so it should dominate the signal. So that's why we were so surprised not to see any signal at all for that case.
Okay, thank you. Oh, okay, thank you.
Okay, I can't see the chat, so I hope that answered the question.
Okay, so thank you very much, David. The only thing I will say now is, yeah, so Peter said well answered. Thank you.
Okay, great. So yeah, and we'll post the slides, okay, Omo?
Yeah,
Yeah.
so we can close it now. There's a representative for Material Research Society. So we thank you for coming. Yeah, so we can close the slide now. So thank you everybody for coming, and it was good to have you. So if you want to have some collaborations with Peter, with David, we'll stay behind, and then we could make a short discussion with David. And so once again, we thank everybody for coming.
Thank you.
We'll be having another talk in a couple of weeks' time, and we'll announce it also just like we did here. Thank you. Yeah.